over to you.
Thank you for your introduction, Susan and Phil. Good evening, everyone. I'm Shengjie Rui, a Merit Career Research Fellow at the Norwegian Geotechnical Institute, NGI. Today, it's my great honor to give this presentation. The title of my presentation is Mooring Line and Anchor-Seabed Interaction for Floating Wind Turbines. Let's start with the development of floating wind. The first question is why we should develop offshore wind in deeper water. For example, the water depth is more than 60 meters. This is because in deeper water have the higher and the more stable wind speed. And 80% of this offshore wind resources lies in deeper water. If we develop this deeper water wind turbine, we can serve some land for this, for example, for this port trade or these fisheries. Lastly, deeper water offshore wind can reduce this virtual and the environmental impact on human activities. The second question is why we should develop floating wind in deeper water. This is because the bottom fixed solutions have some challenges. From the structural mechanics, due to this larger bending moment caused by this wind turbine, these bottom fixed solutions have very long and heavy structures, which will increase the buckling risks and also the rapid fatigue due to this wave cyclic loading. Additionally, the installation of these traditional bottom fixed foundations also have some challenges in deeper water. For example, when we use this monopile. From the cost side aspect, we can find that as the water depths increase, the total cost of these bottom fixed solutions will increase sharply and will surpass the total cost of these floating solutions. Here shows the typical platforms for the floating wind turbines, including this semi-submersible TLP spar platform and the barge. Except for this TLP adopting this vertical tender and tender, the other three platforms are mainly adopt this catenary or semi-total mooring system in shallow water. Currently, there are several floating wind farms are under operation in different countries, like in UK, Portugal, Japan, Norway, France, etc. As we can see, the mooring system have played a significant role in these floating wind turbines. And it has the function to constrain this drift of these floating platforms caused by this wind, second wave, and also the current force. As shown in this picture, we can see when this floating platform have the larger drift, and the mooring line will be tensioned, and finally, all this load will transfer to this anchor in the seabed. As the geotechnical engineers, our main contribution to this floating wind turbines are mainly related to this mooring system seabed interaction, as shown in this figure. This is the main topic of today's my presentation. This is the outlines of my today's presentation. The first part is related to the mooring line seabed interaction. The second part is the Anchor-Seabed interaction, and the last one is the integrated analysis for floating wind turbine. Okay, let's discuss more details. Here, summarize some problems related to mooring line seabed interaction, as shown in this figure. As we can see, during the pretension of this mooring line, the mooring line will gradually penetrate into the seabed, which will influence the load acting on this anchor. And during the cyclic motion of this mooring line, the seabed soil strength will be degraded, and also perhaps the seabed trench will be formed. When we consider this interaction, we need to consider the following impact. Like first one is its influence on this floating structure response. For example, the dynamic force acting on these floaters. The second one is like its effect on this mooring line performance. For example, this load transfer and also this mooring line fatigue life. Third one is related to its influence on this anchor response. For example, the anchor load magnitude and also this load direction. Lastly, it has some influence on this seabed properties, like this seabed trench, perhaps the seabed trench can be formed. For this anchor-seabed interaction, here summarize the main types of these anchors, including this gravity anchor, fluke anchor, suction anchor, or this anchor piles, plate anchor. When we select the different anchor, we need to consider these load directions and also these soil properties. For this anchor installation, we need to consider its material, transportation, installation, and also retrieval. For this anchor performance, like we need to consider its installation effect, load changes, soil degradation, seabed trench erosion, or general scale. Let's discuss more details. Here, as to this chain clay interaction, we can follow the following steps to analyze this behavior. For example, we need to conduct this force analysis for this embedded chain following this equilibrium equation. And then we need to express this soil resistance. We need to consider the lateral movement of this mooring line. We need to decompose this soil resistance in 3 directions. We further need to consider the dynamics effect. So we need to cover this model with this fluid mechanics and also the structure dynamics. As shown in this animation, with the cyclic motion of these floaters, we can find that this mooring line will be dragged repeatedly to cut into the seabed, will degrade the soil strength, and also perhaps the seabed trench will be formed in this area. In West Africa, they have found the seabed trenches are formed in front of the stacked anchor, as shown in this figure, which will increase the risk of this anchor failure. To investigate the formation of this seabed trench, we developed this chamber penetration apparatus, as shown in this figure. And then during our test, we used the camera to capture this clay surface deformation and erosion. At the same time, we measure this soil resistance, and as shown in this figure, we can get how this soil strength evaluate during this cyclic loading. We also proposed this method to predict the final trench profile, considering the mooring line dynamics. We developed this 2-dimensional model and 3-dimensional model to predict the final trench profile. However, we are still struggling to develop this model to predict the trench development versus the time. This is because the complex of this sea state. And now we plan to use this damage model to simulate this soil erosion versus this time. Another part is about the chain-sand interaction. The core question is that how we calculate the load transfer in sand. Like we need to calculate the mobilized friction coefficient between this normal and the actual resistance. Here we developed this chain-soil interaction apparatus. We put this chain in the center of this chamber under a certain confining stress, and then we apply the monotonic and cyclic displacement. At the same time, we measure this soil resistance. We can get this mobilized resistance versus this displacement. And based on our test results, we can acquire this effective width for this chain in sand. And finally, we find this effective width is higher than in sand than in clay. And we also need the reliable method to calculate the chain profile in sand. So as shown in this picture, it shows the mooring line configuration before and after the printation. We can see this chain have a different inclined states. For example, the horizontal chain, vertical chain, or inclined chain. For this different chain inclined state, we need to consider their different failure mechanism. For example, for this horizontal, vertical, and also this inclined. And also we need to consider this uneven stress distribution around this chain when the chain has the penetration. The second part is related to this Anchor-Seabed interaction. Here some list the main DNV standards for this anchor design. including these fluke anchors, plate anchors, and suction anchors. And the target soil is mainly for the clay. Here is this procedure for this anchor design. First, we need to acquire this pretension and the dynamic load at the touchdown point. This is because this different load apply for this different safety factor. And then we need to calculate the tension loss caused by this seabed friction. And finally, we can get this anchor designed capacity considering this material factor. For this anchor analysis, we need to consider its load direction and its verification and its variation. For example, this drag anchor, they mainly used to resist the horizon load, while the suction anchor can used to resist the combined load. And we also need to consider its long-term loading. For example, this cyclic degradation effect and also the benefit from the consolidation. And also its effect from this seabed profile change. For example, the shallow general scale, seabed erosion and trenching, all these tension gaping problems. I won't go more details about these anchors, but I want to introduce, talk more about this shared anchor concept. As now we are developed these floating wind farms. For these floating wind farms, we want to save the total cost of this mooring system. So the shared mooring lines and the shared anchors can be an effective way to solve the total cost of this mooring system. So for this shared anchor, if this 3 mooring line connect to one anchor, maybe we need this structure have these symmetrical structures. Perhaps this subla and the fluke anchor is not the best choice. We also need this anchor to resist the inclined load. And also, this anchor needed to resist 20 or 25 long time loading. So after this analysis, we find perhaps this gravity anchor or suction anchor or anchor piles can be the better choice. In fact, the suction anchor has been adopted as the shared anchor in high wind tempen, as shown in this figure. We can see that under this condition, this anchor needed to resist 3 times of this uplift load. Under this long-term cyclic loading, for example, 20 or 25 years, perhaps there are some tension gaps, or this seabed trench may appear around this suction anchor, which will bring some risks for this mooring system safety. And here we proposed a novel casing plate gravity anchor as the shared anchor. Here shows the main concept. It's the combination of this, the gravity plate and also the suction casings. It has some advantages. First, it can have increased capacity due to this coupling effect from this plate and also this casing. And also, after this peak capacity, this type of anchor still have a higher capacity, which means it have a higher reliability. And also, due to the effect of this plate, we can move this pad from beneath this seabed to the mudline, which can inhibit this seabed trenching or this tension gaping problems. We also plan to install this kind of anchor by itself weight, so that we don't need extra equipment. And we also designed these procedures to balance the installation and also this capacity by optimize this anchor configuration. For example, we can adjust this plate diameter and also the casing diameter and also this penetration depth. Part of this work have been published in Geotechnics in the latest issue. Okay, the last part is about this micromodel for integrated analysis for floating wind turbines. Here shows the mooring system for floating wind turbines. In the traditional method, they mainly assumed a fixed point on the mudline. They use this elastic spring to simulate the seabed response on this mooring line. In fact, the embedded chain will cut into the soil, which will influence this seabed friction mobilization of this lane chain. So here summarize some benefits from this integrated analysis. For example, we can use it to get more realistic dynamic motion, including this more accurate marine line dynamics. Or we can use this to directly simulate the seabed trench or soil degradation. And secondly, we can use this tool to optimize the mooring design in a direct way. For example, we can direct get this mooring line tension and the tension loss, and also direct to determine this load acting on these anchors. And also, we can use this one to analyze this anchor post-failure behavior. Here, we mainly use these micromodels to simulate the mooring system seabed interaction. Here, give an example for this suction anchors. We use one micromodel to simulate its behavior under this inclined load. For more information, Zefeng tomorrow will give this presentation to introduce more details about this micromodel for suction anchors. For the micromodel for the embedded chain, due to the larger deformation of this mooring line, we need several micromodels to simulate each segment position. So for more information, you can refer to this ISFOG paper. Here shows the main results under this static analysis. The traditional method, they assumed a straight line in the water, and then they will connect two ends. One is to this pedi on the mudline, another connected to this fairlead on the floaters. Our method will simulate these three segments, like this lane chain or also the embedded chain, to simulate the realistic installation of this mooring chain. So the static results here shows the main static results, including this mooring line configuration and also the mooring line tension. We find that the embedded line will influence the line configuration. It will increase the fairlead tension on the floaters and significantly reduce the anchor load depending on this water depth. And we also conduct this dynamic analysis. We analyze this, we conduct this dynamic analysis under this operational and practical conditions, considering these different significant wave height, the wave period, and also this wind speed. Here shows the main results. Here shows this fairlead and pedi tension in time domain. Here shows the main line tension change at a different time, and also this seabed friction at a different time. We also find that the embedded line will increase this fairlead dynamic tension, and near this touchdown area, we find this reverse seabed friction. And we also find that this seabed soil strength can be changed during this cyclic loading. Here is the summary of my presentation. The first one is related to this mooring line seabed interaction. We need to consider its impact on this floating structure response, the mooring line performance, and also this anchor response, and also this seabed properties and profiles. For this anchor-seabed interaction, we need to consider this load direction change, long-term loading, and also the seabed profile effects. Traditional method faces some challenges at the shared anchor. Perhaps this casing-plaved gravity anchor can be an option. And for this integrated analysis for floating wind turbine, micromodel can be used as an effective approach to simulate the more realistic behavior of these floating wind turbines. Embedded line will influence this mooring line tension under both static and dynamic conditions. For more information, last year we published this review paper entitled A Review on these mooring lines and anchors of floating mooring structures, which including these floating structure applications, including this floating wind turbine, and also the platform classification and also dynamic characteristics, and also this mooring system scheme, and also this mooring line static and dynamic analysis and anchor installation and performance evaluation. This part of work gets the support from European Union and also the Research Council of Norway, and get the support from Dr. Hans-Peter Justet and Dr. Zefeng Zhou at NGI, and Professor Li Zhongwang and Professor Zheng Guo at Zhejiang University, and Professor Aaron and Professor Seven Sevic at NTNU. That is my presentation. Thank you for your attention.